Everybody, thank you for coming. This is an evidence-based toxicology author publications webinar series from the journal Evidence-Based Toxicology and also kind of supported by the Evidence-Based Toxicology collaboration. And today we're going to be talking to Lena Schmidt about her work on automating evidence synthesis in the course of doing living evidence reviews. Lena's very experienced in using automation tools, so all kinds of digital evidence synthesis tools, but in particular, recently, large language models. So we're going to be discussing what AI really means for the automation of systematic review. So Lena, if you would like to take it away, I'll just stop sharing my screen and you can jump into your presentation, please.
Thank you very much, Paul, and I hope that you can all see my screen right now with the presentation. So
Yes.
So this webinar, and thank you again so much for inviting me. So this webinar is about a commentary paper, which we recently published in Evidence-Based Toxicology, looking at 17 LLM automation papers that were found in the scope of a living review and looking at their methodology, evaluations, lessons learned, and some of the caveats. So briefly about me, I'm currently finishing my PhD at Newcastle University. I'm really interested in automation for systematic reviews. And I recently started a position as research fellow at the Epicenter at UCL as well. And yeah, looking at research that make reviews living, research into how we can not only do that for systematic reviews, but also like more rapid reviews and evidence maps. And the commentary paper that we'll be looking at today basically looks at what are LLMs, how do they work, what are they good for, but also looking at some of the hype that's been circulating and some issues where we should be concerned and some where, we may be not as concerned. So just to briefly start off with a little bit of a history about natural language processing. So about 20 years ago, these numeric representations of text that natural language processing is looking at, they were quite simple. So what we have to understand is that computers can't actually handle text. They can't really understand text, and they are calculators. So what was happening is that the computers or algorithms, they would look at sentences or documents, they would count how many times words or phrases appear in them, and then they would create these long lists of numbers and counts and normalized versions of these counts called a vector, and then to train some machine learning to differentiate between documents, for example, doing simple logistic regressions. And the issues there were that these lists can be very long because many words exist, and there was no meaning really associated with the words, and the words weren't in a particular order. So you can see in this example here, for example, the dimension of the vector that represents the word basketball, there's quite a strong representation in one sentence, but it's like less strong in the other sentence. So based on that, one can train a logistic regression classifier, but this is just quite limiting because there's no representation in the relationship between words and neighboring words. And one way of solving this were models like Virtuec. They look neural networks to look at like co-occurrence of words to train some of the first embeddings that convey real relationships. So if you represent these documents as text, you could plot them, and then you can look at the angles between words. You could plot them in the coordinate system, and you could see that this angle between the words actually reflected their relationship. So man has the same angle to woman, and then king has the same angle to queen. Based on that, it was possible to train deep neural networks, but there was still quite a bit of limitations around, and that's because there's only one embedding per word. So if you look at the word fan, for example, your desk fan has the same embedding as a heavy metal fan. And so thus, the neural networks based on them were quite limited. And then what happened with LLMs is that a new technology came, and that is called the transformer. So this was developed around 2017, and it just represents text much better because these embeddings aren't static anymore. So they are still a bunch of numbers that represent a text, but they can change based on context. So what happened was people started to collect giant amounts of text. And our example here, for example, our example text is books usually contain pages. And then the large language model would mask out a word and then train to predict the masked word. So you'll basically end up with a statistical likelihood of what is the next word, and the neural network can pick the one on top. So there are, of course, many options fitting the answers in that sort of training example, but the LLM will just adjust itself to bring the most likely relevant options to the top, and then it will be able to predict words in a sequence. So there are two different types of LLMs. So there are these smaller discriminative models, like for example, BERT, you might have heard about them. And they are these small pre-trained language models, or PLMs, how we can call them. And they are content with outputting these sort of number representations of text so that further neural networks can work with them. And then there's the generative LLMs, such as GPT models. They kind of just have the ability to convert the numerical output back into plain text for the user. So if we briefly look at how these types of automation were integrated into systematic review automation in practice, the most mature type of automation that many of you will probably know because they have been integrated in many screening tools is machine learning for reference screening. So the way how this is integrated into the tools is that the tool can learn from the screening decisions made by the users on the go. And it uses actually these simple vector representations from 20 years ago to train models like the logistic regression. And it's quite easy to validate them because you can validate them based on fully screened data sets. And it's also a pretty low risk automation because reordering references lets you review the likely relevant papers first. But that means, of course, that you still need to actually manually save or screen the papers. So there are ways of saving workload, but this just depends on how much risk you can take and what the review methodology allows. So for example, you can if you have like a dual screening workflow, you can switch to single screening once the frequency of included records declines. And then there's also some current really cool research on additional algorithms that use some statistics and distributions to estimate if you can stop screening early, or you can estimate how many included records there are left. So overall, these are quite mature and usable and well integrated in tools, but there are limits to their performance, and it's not really possible to generalize their safety because they're all just dependent on the sort of context that the review is in. Automated data extraction using sort of the older LLMs, the pre-trained language models that just work on the numerical representations, that's an area also with lots of research because we do have labeled data sets, we can fine-tune models, and since they classify existing text, it's also quite easy to run evaluations. So you can use that to classify documents for evidence mapping, for example, or to mine data from text. They're quite customizable. You can download them onto your computer and it's easy to evaluate. Or you can use for training custom classifiers for like maps, evidence maps, or basically take large corpora such as PubMed and label them and provide them in terms of like structured search engines. So this sounds great, but I think there are about like more than 100 published papers on using exactly these kind of algorithms, but they haven't made their way into practice. And that's because you need some data science knowledge to run them. They aren't quite flexible to be integrated into big end user tools. So because in practice, I think in automated data extraction, we need to identify things like intervention arms, and we need to identify outcomes, and then we link up the data. And these models aren't good enough for that. Plus, they are small and domain-focused data sets, and basically they are just not really representative of the whole of systematic review automation, so it becomes tricky to integrate them into practice. But then, as we all know, in 2023, this generative counterpart of the discriminative language models had this hype. And scientists were quick to pick up on it because the text produced by like ChatGPT and Co., I mean, it's really good and it sounds really plausible. So the hope really came up. These models can already understand our systematic review tasks, and we don't really need to train them any further. And they could also almost instantly fill some of the gaps by older models that can't judge complexity to find links between data, to link intervention arms, to link outcomes, etc. They were doing very well without any actual training. And also, of course, really easy to access. Everybody can run preliminary tests on them, and then all of that just makes them really promising. Especially if you look at it in terms of living reviews, where we do want to keep evidence up to date and relevant. And then I think generally just outside science, but in general there was the hype. People started using the LLMs for day-to-day tasks, and then I think some scientists will probably also there might be like some degree of fear missing out on automation, but then also to be more open towards AI because the hype was just everywhere. And then secondly, of course, there's marketing and investment factor. So the technology is so present in us hearing about the immense amount of money being invested, just kind of gives us a sense that this technology should hopefully be future-proof and must be good. But if we look at the actual research that has been published, so the 17 papers included in our commentary review, there are some really big recurring problems. And the first one is, of course, that we do need to validate the LLM output. And just because we don't need a big data set to train it, that doesn't mean that we don't need a big data set to validate it. So LLMs, they use these zero and few shot learning, and they're being tested on super small data sets right now. And those can be quite unrepresentative because sometimes they just originate from a single review. So small data sets back then were one of the most cited issues, while the older technologies couldn't make an impact. But these older technologies and those data sets were actually much bigger than what is used to validate the LLMs now. So that is an issue because these prompts that LLMs are based on, they just don't generalize very well. And LLMs change, so there's new effort with every review and across time if the underlying model changes. And machine learning and older models did not really have these issues because we could actually download the whole pre-trained models, and they weren't, so big, and they weren't changing very much. Additionally, there is quite a high evaluation effort because in screening tasks, it's still easy because they're binary decisions, include, exclude. But for data extraction, when the output is generative, it's actually not as straightforward because the older models, they didn't have this issue because every word-based classification can be run and compared automatically to a gold standard, and models could be retrained and evaluated. But with LLMs, because they're generative, they create new text. There's a risk that if the properties of a model change, that then some manual evaluation of matching the extraction has to be repeated. So early LLM papers, especially in our commentary, they needed to make any evaluation task binary. So even if it's some complex data extraction, they were asking, is the information extracted correctly for a document, yes or no? And they would validate that with accuracy. Previously, like with the other pre-trained language models, there was binary evaluation, but it was on the word level and not on the document level, which is actually much easier because which is much harder because for the LLMs, it's much easier to getting a human to judge if something looks all right versus actually classifying every word correctly in a text. So that is why it's actually quite hard now to see or to get some consensus of how do we actually evaluate AI and how well do we need it to perform in order to be accepted into practice. And then lastly, I think black box hallucinations, heavily automated tools with auto-synthesis, there it's really hard to spot if an LLM actually hallucinates. So maybe it's a bit paradoxical and confusing that LLMs suffer from problems that were often already addressed by older models, but these older models really weren't good and flexible enough in practice to provide, like a step change in automation, really. So looking at this Gartner hype cycle, we can see it's estimated that generative AI has actually passed its hype and it's gone into this trough of disillusionment. And I think I definitely wasn't there in this draw of disillusionment as the start of 2025, but now it's quite clear that it's time to move on to use the LLMs responsibly and safety to reach this plateau of productivity, so to say. And the hype train there, I mean, it's obviously left the station, and there are quite a lot of startup tools and content creators that have really started pushing these narratives, like the 10-minute systematic reviews. And in some of these videos, they go so far as to mention all the relevant concepts. So they mention PICO, systematic search, Prisma, Cochrane Handbook, and they call their work a systematic review. So it's probably a little bit of a cowboy methodology there, like a cowboy methodology approach to systematic review, because the results of this aren't actually systematic reviews. They're rapid overviews and summaries, which isn't too helpful for those of us who are actually interested in health-related research that can like feed into policy making or decision making. And LLMs, I mean, they can not reliably and scale author synthesize at this place. And they would usually weigh evidence wrongly, for example, take expert opinion on text from random health-related blog posts and websites as serious sources of information, and then they'd weigh them as important as the conclusions from a published review. But their autosynthesis is, of course, more timely, but it might just be incredibly biased. And the other day, James Thomas actually did a presentation about a similar topic. And he mentioned this quote from a paper, or was it an article, that talked about the craziness of how AI can make systematic reviews in the time it takes you to drink a coffee. So I tried to find that on Google yesterday because I couldn't remember where it came from. And then this is what I got, what you can see here on the screen. So Gemini AI gave me this wonderful unsolicited answer that looks at all the wrong parts of my query. It chooses its own research focus, so it says a 10-minute systematic review isn't crazy because coffee can boost your productivity to do it. And it even gets me this nice scientific pathway with blocking adenosine, which in itself is probably correct. It just doesn't really have the causal connection to speeding up systematic review. So I think this kind of illustrates the issue with LLMs. They're based on the statistical co-occurrence of words, and they're biased towards commonly occurring topics in the training data. And I guess coffee is just simply more popular than the hype 10-minute review. So the LLM's attention just shifts away. And in the large autosynthesis, scientists can't really control the issue. So, but this doesn't mean that LLMs aren't good. We just need to use them correctly for screening and data extraction with better or cleanly defined methodologies. So with autosynthesis off the table, I think we can use LLMs very effectively for screening and data extraction. I think a lot of the current research just shows that. So they can automatically categorize evidence into buckets for evidence and gap maps. They can be tested for replacing one person during screening and maybe replacing one person during data extraction, and then they can be used to pre-populate data extraction forms. And we need more work in making complicated data extraction work. So for example, linking outcome data to intervention arms. And then maybe after that, we can revisit the autosynthesis. But in order to be able to do all of these things, I think in theory, we can definitely do them. But in practice, when we use it in projects, we have to follow really rigorous methodological requirements. And I'm really simplifying this now quite drastically. But in order to really effectively use the LLMs, we need to make sure that, of course, our searches for the evidence are rigorous, and then we do still need human labeled data. So we can develop and independently validate prompts. Yes, we don't need to train, but we need to develop reliable prompts, and then we need to be transparent in the reporting. So we need to report which LLM was used, for example, to report the actual prompts, and to use commonly accepted evaluation metrics as well. And a lot of the how-to of actually do that will be covered in the RAISE guidance that a few of you will probably have already heard about, so I don't want to expand on it too much here, but it's a guidance for reviewers, methodologists, tool developers, and others to others with like interest in the evidence synthesis ecosystem, and it will give a good theoretical background how to actually basically responsibly and ethically use AI in evidence synthesis. And in practice, there are other initiatives. So, for example, ESIC is something that many of you will have heard of before, the Evidence Synthesis Infrastructure Collaborative, who will provide funding and support for exactly this type of method development, help us to hopefully unite some efforts to make sure that exactly these areas here on the left, where we should be able to use LLMs in practice, will actually get ingrained into practice, and that we will be able to soon hopefully reach this plateau of productivity with the LLM usage to actually speed up our systematic reviews. That's it from me for now.
Very good. Thank you, Lena. So we're now going to have a bit of a chat about a few things like around systematic review, because we have obviously the pleasure of hosting Lena and her general expertise in this. And we know that there's a lot of stuff, a lot of concerns, a lot of things that people think. So we're going to talk a little bit about hype and some of the frustration around systematic reviews, I think, Lena. We'll talk a little bit about what LLMs like really do and why they can maybe kind of confound people a bit because of kind of the way that you interface with them. We'll talk a little bit about performance testing because we're nerds and we like that kind of thing. Tuning and training will probably come into that, and then probably talk a little bit about ethics potentially of like using tools which may not have been created entirely ethically themselves. But we also very much want to hear from people in the audience as to what you would also like to hear as like opine about in the next 20 minutes or so. So if you've got any like topics or themes or anything you'd like us to touch on, or any specific questions, there's a Q&A that you can drop questions into. You can just drop questions straight into the chat if you prefer. And we'd very much like to hear from you and hear what you have to think. So maybe, Lena, shall we start with a bit of the hype, a bit of the frustration, shall we? Because, yeah.
Yes.
Oh, yeah, sure. Because like it's notable, like in my interactions with people, like when I venture into social media occasionally, that people get quite cross about large language models, I think, for a number of reasons. And also people obviously get very overexcited about them for a number of reasons as well. I think most of what I see is complaints rather than necessarily people like thinking these things are wonderful. I think part of the hype might be that you get, a lot of the marketing and a lot of the stuff that you see where people are saying like we should be using large language models comes from more communication and PR aimed at getting investment, maybe, than necessarily explaining to people what they're actually good for. And when people try to use them, because there's not much communication or training in what these things are and how well they work, they get quite frustrated quite quickly because they do things that I would think would be quite weird to ask a language model to do at all, right? Like I have a little bit of experience in linguistics. I have some amateur training in computational linguistics. And when people talk to me about large language models, I annoy them by shrugging because it's just like doing more numbery stuff with words. So I don't get particularly excited. I just see a tool that allows you to do certain things better. And I see a researcher using that tool for a thing that tool is not designed for. And then the researcher gets annoyed with large language models. And I just think, oh, this isn't the right way to proceed, is it? So in your sense, like what do you think like a large language model is actually good for? Because we're talking about like generative text technology, right? It's predicting the next token. So with that in mind, when you're doing a systematic review, for example, what would you expect it to be good at, and what would you expect it to be bad at?
Yes, and I mean, that's exactly what you're touching on, this generative nature and the large language model basically just being the statistic model that gives us the most plausible output text. But then at the same time, it's just so good. Like what it gives to us, the output text is so good. And that's why I think where it comes from that many researchers, they try and skip the normal steps of the systematic review of, reference searching, of screening, and they try and skip into this auto synthesis mode, because I think that this is something that the large language models are made for, right? They were made for summarization, and this is why people try to apply the large language model, and that's why they then get frustrated, because with their rigorous research background, they will then just realize that in our case, in research, like LLMs aren't any good for this. So I think what I quite like about the large language models and where I think are its general strength is just this I guess skill, or not skill that they have, but like the way how they can actually understand the questions, or not understand, but how they pick up the questions that we want to ask them and then apply them, for example, in the screening scenario. Because with the older models that relied on fine-tuning, we just used to have to give them so much training data in order for the models to sort of gain this this sort of skill of sort of representation of what does the user want, and then to be able to make the prediction. And the large language model, what I think is so exciting, is to be able to skip that step. So to just be able to explain a research question, just like how you would, for example, explain a research question to a person helping you screen a systematic review, and how it is actually able to pick that up and then to just apply that downstream relatively quickly without you having to, you know, set up a whole lot of like data science workflows on your computer. I think this is, you know, like this ease of actually pointing the model towards what it is supposed to do. That is really exciting, because in screening, of course, yes, but even a bigger problem, I think, an even bigger unsolved problem previously was data extraction, because we used to have to use these huge data sets just to train a model, for example, to pick up a population, or to train a model to pick up an intervention. And these are some of the most basic units of data extraction in a systematic review. But then in practice, you have so much other data extraction that you need to do. And all of this data extraction will be very specific to the systematic review that you're doing. And we were just always guaranteed to not have enough training data to train these models. So the fact that the LLMs can do the 0-shot or 1-shot extraction, even for our more rare data extraction questions, I think is the second thing that excites me most about them. Because
they get better over time as well, right? So I think like we learn to be frustrated very quickly, and you look at a technology a year ago that was just producing preposterously dumb stuff, and then we think it's the same technology now when it isn't. And like people are very well aware of a lot of the problems that like predicting the next token, or the like what is on like what would the on average the next word be, right? Is very useful, but you have to like learn how to constrain the predictions, and make sure the machine knows what domain space it's working in, so you can put an edge like on the field that it's running around in. And if you can do that, you can start getting quite like, if you ask like, you know, the topic that a paper is about, or the people that talked about a paper, something in those contexts, like predicting the next word can be very helpful. I use it like a lot for, it can be very useful for context, for example. So we're looking in publishing, which is where kind of as an editor I work mainly. We're looking at how we can use LLMs to have access to domain knowledge that you can't have as an individual person, because no individual person can read 20,000 scientific papers. And then if somebody submits as a paper and they make a claim about something they've done that's novel, or a change in the state of the art or whatever, we can compare what they've claimed in their paper and look for similar claims or knowledge statements in other papers, and actually have a way of evaluating like how true those claimed advances are, which is really good.
That's summarizing. That's not systematically reviewing, Paul.
No, it's not. No. But that's the thing. These are summarization engines. They're not evidence synthesis engines.
And it's about productivity, right? I think that for the language people, what the marketing people, what came to their hearts was the way LLMs talk with you. Oh, the outputs are so nice. Yes. For us systematic reviewers, is the amount of things it can do, right? It can save me a lot of hours of time. Yeah.
And how Paul says how it then sort of enables you to also cross-reference with this information that's been, I would say, like latently stored within the neural network due to its pre-training, where it was just predicted, where it was just trained to predict what comes next. So this whole sort of knowledge that is stored within the network is then obviously like really, really useful. And I mean, I can definitely see, I definitely feel with you there where you're saying, Paul, that like people or researchers quite often claiming a lot of like novel contributions or a lot of unsolved research, because I can see that in the data extraction papers that were part of my living systematic review, because I had 117 papers on automated data extraction, where I think almost every single of these papers have really claimed to do not only like a novel thing, but also to be better than anyone else. And but if this threshold of like this exceeds of like 100 people sort of claiming the same things and doing the same things, it becomes, I think, quite difficult in practice to keep track on that. So if you have this I guess like auto summarization or pointing you towards evidence, I think it's quite useful when you're maybe thinking about setting up a research question, you're mulling over it in your head, or you're looking at it from the perspective of a publisher. I think it's quite useful. But I think the way how this is useful is just so many steps before the actual systematic review process starts.
So maybe we should get to an audience question here, because we have one. Sorry, Patricia, can we
I was going to call for that question, because I think people would like to have examples of the real life. We were just talking about that before starting your systematic review. What can you do with LLMs? So Philip Tadger is asking, building on the previous question about what tasks LLMs are good or bad with, which specific models or software, GPT, Claude, Gemini, do you have good experience working with? Do you recommend to local models or cloud-based models? Can we use Gemini as you did in your presentation?
I mean, I think I would probably so for me, I'm maybe a little bit more critical of the automation than many other people. So I do usually use these generative models just to like rephrase my English. So for example, if I'm writing like the protocol for the research paper, I don't think I have ever used generative AI to actually do the primary work of finding relevant references for me. I've usually just used it to make the text that I write more interesting.
Can you give examples of tools you can use for screening, for example?
I mean, so for screening, as I said, there is the non-LLM based active learning, which is just really mature, and it's integrated in all of the it's integrated in all of the systematic review tools. And then I think some of the bigger systematic review tools that are out there, like for example, with an EPI reviewer, there is an integration of large language models where you can ask it to do binary screening decisions. And I think probably, you can directly query the APIs of the large language model providers as well if you have your own data set. So this is something that is fairly accessible to people, I mean, especially for screening. But I think just the pure integration of this LLM screening in a tool doesn't actually make it usable, because everybody can now go and can, ask a question and extract some data and store the sort of LLM based extracted data in a tool. But what we really have to do is also to validate it, because if we don't really use like a good methodology to validate our screening automation, then in the end we just risk sort of biasing our whole systematic review.
And I guess the rule of thumb, right, is probably don't use an LLM for most systematic review tasks, because the other technologies are more established, better validated, more transparent, and produce better results. Like the data that we have on LLMs, when you like look at, say, the performance metrics that some of the big LLM-based evidence synthesis platforms are promoting, the measures they're using are quite difficult to interpret, and the data they're putting out is questionable, I would say, at best. Whereas established systems probably use a better fit technology, and that if you're thinking about using an LLM for systematic review purposes, you probably shouldn't be. Would be more or less the bottom line, because it's just not the right kind of thing. Like, being able to predict the next token is not very useful for determining fit between a reference and the research goals of the project, right?
Yes,
like, you might be able to summarize. Yeah, sorry, Lena, take it away.
Yeah. No, I definitely agree with you. I mean, I do think that we can use an LLM for screening in a systematic review, but we have to keep in mind that this is right now for a research purpose still. So, you know, we shouldn't just go and blindly use it, but if we actually use it, what is great is, for example, say like you're in the context of doing a living systematic review, which usually means that you have like a base review. So you have the first iteration of your review, and then you're expecting in the future to do updates. So say, for example, if you are in this sort of little universe where you've got your base review finished, you can then, for like a research purpose, use your screen data, and you can then develop some prompts and you can test and evaluate the LLM. And then you could do something like, for example, running automated updates autonomously. You then, of course, before you do a full review update, have to manually check some of those. You also have to make sure that when you assess your model on your base review, that you're looking at things like sensitivity, that you're looking at things like precision, because you want to know how many relevant records are actually retrieved, you know, how many of these retrieved are actually wrong. So key metrics like that are, I think, quite important. And then also to be able to, you know, discuss this and to say, look, I'm doing my living review and I am providing maybe on a dashboard, etc., some automated updates, to then say how well did the model actually perform, and then also to have a very clear sort of methodology in mind of how for review updates this is going to be checked. And I think the same thing applies for evidence maps as well, where you have a little bit, I guess, like lower stake research question, not like low stake research questions, in the sense that you're not really directly trying to inform, you know,
quality
evidence-based practice, but you're actually more or less looking to gain like overviews of evidence in a way that is much more rigorous, I think, than these fully synthesized reports.
Yeah.
Okay, so maybe we can move on to another question. I think we have quite a good audience of systematic reviewers, so we can probably be quite technical here. So Gisleberg Helland, I apologize for mispronouncing, asks, have you had any success implementing retrieval augmentation in your work, either RAG or CAG?
I have looked at RAG specifically. So basically the point, I think, maybe I should expand a little bit on this. So the point of this retrieval augmented generation is to be able not to feed like a whole huge document to the LLM, but to rather basically prioritize different sections of documents to make the LLM look at these sections, and then to extract exact pieces of text from these sections. So I haven't implemented RAG in a huge system yet. So for example, where, you know, the document is so big that I cannot I guess, fit it into a whole like large language model. But what I've done is that I've just tried and forced the LLM to extract data verbatim. So basically, rather than, you know, going and not giving the model any context, I would have given it my whole input document as context, and then told it to extract pieces of information. But then rather than treating those extracted pieces of information as the final output of the model, just tried and did some matching to make sure that the text wasn't hallucinated. So I think for this, in terms of like trying to prevent or, you know, keeping hallucinations to a minimum, I think RAG is quite a good approach.
And I guess it's maybe we can digress slightly into exactly how the computer is thinking here, right? Because Patricia, you touched on it a minute ago when you were talking about how the marketers get excited because it feels nice to be talking to something, right? I think there's something a little more fundamental than that, which is that what makes LLMs unique is for the first time ever, we've got a natural language interface for computational functions. So you don't have to be an expert in a piece of software even to get a computer to do something for you. You can tell it how to do something in the same way that you and I would tell each other to do things, right? And then we go off and we act as agents if we want to be technical about it. We go and do the thing, we come back and give the results, which is lovely. But like, we shouldn't think that computers are thinking in language like people are thinking in language, right? And because we interface with the computer using language, that they're not on the receiving end like people at all. They turn language into numbers. So they create a statistical model of what was said, and then they have to figure out relevance and attention and whatever from patterns in those numbers, right? So giant matrices of numbers. So, I mean, Lena, I don't know if you want to comment on this, but like when a computer pays attention to like a paragraph in a document when you're telling it to do it, it's not understanding that it's got a document in front of it, and it's not counting down the paragraphs to see where the paragraph is. It's got a numeric representation of that document, and within that numeric representation, it's got a statistical concept of what a paragraph is, and it tries to find them through the translation of numbers and then translate back to you into language again. So you go language, numbers, language. So anything to say on that? Or was that, do you think that was sufficient?
I mean, no, that makes absolute sense. And I think that is one of the core issues. While sometimes, you know, the auto synthesis or these LLM mode in our Google browser, that's why sometimes it just fails spectacularly, because it does know, for example, which documents to look at. So it does know that if you ask it a health-related question, it will look at like published scientific papers, and then it will look, as you said, like it will look at the paragraphs. It will look which of the paragraph mostly sort of corresponds to your answer. But the model then doesn't understand, and it can't really weigh where is the information coming from and what's the relative importance of the information. So it might then go and look into in the introduction of your systematic review where the reviewer has written a hypothesis, and it will extract that as a statement.
So I would go further,
exactly
right?
It doesn't, right?
The metaphor of looking doesn't work for the large language models because they don't look anywhere. They're not humans with eyes that look at a bit of a document. They have a complete representation of the entire document space, and they match statistical models of the thing, that the concept that they're trying to find in that space onto that space and take the best matches, right? So they don't look at the introduction. They match a numeric shape, if you will, onto other numeric shapes in the system through like a pattern matching exercise, essentially. So this idea that they're looking, again, it's like a personification or anthropomorphization rather of what the machine does. So if we understand that the machine isn't thinking like a person, it's not looking at things, but it's pattern matching through statistical representations of linguistic spaces, I think it's easier to understand why and how these things get things right and why and how they get things wrong and what they're useful for, right? Like summarization is patterning, and that's why they're so good at it. But like finding, like even when people say, like, you know, it's even more, I suppose one of the things that's kind of funny is that when people say that, well, you know, this machine learning things, LLMs got better at which citations it's looked at for this knowledge claim that it's fed back to me. So like the caffeine thing, you know, have the little citation on it. The machine hasn't read that citation and looked for the information in that citation and then reported it back to you. That citation just has a good statistical pattern match with the information that it has reported back to you through its prediction of what the next token is, you see. So it's not used that data in any meaningful way like you or I would use that data. It has found a match of a document which has data in it, which matches the data it's fed back to you. So it's not citation in the sense that you and I or other researchers would mean it, I think. It's a completely different thing. But anyway, we should probably answer another question that's much more systematic review.
Yeah,
so
take the one by Eva.
Eva, okay. So, Lena, could you please talk a bit about how a large language model would work for data extraction, where you usually would have several items of interest, so PICO or PAYCO data, risk of bias methods, numbers representing estimates or effect associations. Is that possible as of now?
Yes, and I think it will depend on how you set up the large language model. So at the time when we did the commentary and we looked at, I think, the first 17 or so papers that were published on using large language models for data extraction, that really wasn't possible because quite often the LLM would just return its summary. So if you were asking it about intervention arms, for example, it will just give you one blob of text and you would say like there's one arm here, one arm here, one arm here. But anything really that it had quote unquote extracted, you couldn't really call it extraction because it was really just a summary and you couldn't pinpoint where does the information in the paper come from. Does it actually exist, or is it just something that the LLM was, I guess, predicting as its sort of likely sequence of tokens that was basically just representing well what is done in the general research space, right? So, but now, more recently, it's become much more possible to get the LLM to actually return the text as it is in the document and to ask it even to return specific data types. So I can now basically query and prompt an LLM to return to me a list with intervention arms, and I can now also tell the LLM to please return it as is in the text. And then I think through multiple workflow steps, you can then work on reconstructing sort of the picture that sort of makes the data extraction for the systematic review. But I think the big caveat there is that this is probably still a little bit more work intensive than just doing it manually by yourself, because you will have to validate this, I think, quite rigorously. You'll need to do a lot of checking, and for that you will have needed to do the data extraction first manually. And you know, the prompts that you do on one data set, they might not very well translate to a different data set. So yes, I think while it is generally possible, I think we are still stuck in a little bit sort of doing it in a research context. But at the same time, I think what I can see, or what I can hope with some of the systematic review tools that are integrating LLMs for data extraction, is that we will sort of transition to using this as a semi-automation. So to set up our structured data extraction questions, to set up our sort of data extraction forms in our tools, to have the LLM auto-populate it, and then to be able to you know, at least for like one reviewer to verify and to change, but yeah, but to actually use it in the semi-automated way for now.
So that's, I mean, that's a good point. So there's an analogy to data extraction. Like we've got a paper in the evidence-based toxicology at the moment from some researchers at RIVM in the Netherlands who are looking at how to take a study or other documentation like a preprint or just some internal like laboratory documentation, feed that through a large language model to automatically populate reporting checklists, so you can make sure that you've provided, if you're trying to do, say, like an OECD guideline toxicology study, that you've provided all 73 types of information or pieces of information that the OECD would need in order to evaluate your study for regulatory purposes. So that's very analogous to data extraction, obviously, because you're taking pieces of information out, putting them somewhere else. That's much more structured because you have one target, right? That the machine can learn. You're not creating a new target extraction every single systematic review that's different, right? So in that sense, it's a bit easier to validate as well and kind of see how well it's working, and easier to train. But these systems are getting much better, and that system already has about 70 to gets it right about 70 to 80% of the time, depending on how you measure it. And that's looking very promising. I think we probably have time for one more question before we stop and let everybody go just before the top of the hour.
Get the one by Marcos, because it has been commented and liked.
Oh, good. Yeah. So Arkosh is very complicated question. Which one was that? Sorry.
We are exploring beyond these usual suspects as well.
Oh, yes. So, I mean, Arkosh is co-president of EBTC and works at, or maybe until recently, he's worked at the European Food Safety Authority and does a lot of stuff and specializes in this and knows way more about these things than I do. Uh, Says there are good experiences with Llama, tokenizing PDFs, DeepSeek just published a new model, might be good for optical character recognition, processing complex tables. Should we just finish with tables, right? Because this is where a lot of this stuff started, like back in the day. Tables used to be a complete nightmare, right, for automated data extraction using in the dark days before large language models came along in 2022, 23. Lena, did you do any work with tables back then? And are tables easy to deal with now?
I actually did not attempt the famous tables. I mean, I do know what happened if you try to do PDF to text extraction on tables, and you'd end up with a soup of characters and not being able to identify clearly where is the information in which column, what goes where and what belongs where, because tables, they can obviously be almost infinitely complicated. I just know that of course with also applying LLMs, mixing LLMs with OCR, it's now becoming much easier to actually get the table output from the PDF in a structured form. But yeah, I can't say much more than that because I think it is still a very complex research topic that I actually haven't attempted.
Okay, do you think it should be a concern by future authors of trials and studies not to put things on tables that they are picked up by LLMs later?
And I mean, that is a really important point that you raised there, because of course, if authors of studies, of primary studies, were sort of able to put the data into some repositories where there's like a predefined structure and to share their data like this, freely, then it would be much easier for us doing the primary reviews of doing the systematic reviews to access that and to import the data. Of course, we always need to do some like double checking. We need to make sure that everything there is all right as well.
And you have to do that individually for each paper. Go to the tables shared and upload it.
Yeah, but I think it would, of course, be the ideal scenario where the trial authors would be, depositing the data in a machine-readable format. And they could, of course, still report it in their paper, no issues, but it would be nice if it was also available in a more structured format. But I think there we are probably going beyond the sort of systematic review automation issue and probably like moving more into something where maybe publishers should demand for trial authors to do. And I think I agree, it would be great.
So I think just to touch back on that, because you mentioned PDFs in the same breath as tables, right? So maybe what I meant was, like back in the day before LLMs, we had this terrible problem with PDFs, right? Because in a PDF, it's very hard, particularly for like typical NLP processes. Like the PDF data structure is terrible. You don't know what word is where. There's no map for what's even a word on the page because it's not really encoded as words. You have columnar layouts, you've got weird tables. So unbelievably difficult for the computational methods for extracting data to deal with at the time, to the point where we're thinking, back in 2018, 2019, our discussions were about how we retire PDFs, which seemed difficult because getting people to stop using the most shared document format in the entire world in the history of everything was going to be quite challenging. But that was what we could think about as a solution. Now we've got LLMs, we actually have an end of pipe solution to the problem of PDFs and tabulation, because it looks like we can get the LLMs to do a much better job of tabulating data for us from messy PDFs that will obviously not completely solve the problem, but will solve the problem a lot better than trying to get every individual researcher to put their data into a repository in a structured format, because that is reaching like however many million researchers there are and getting them all to behave differently is entirely impossible. So I think we'll end up somewhere better as a result. So I think on that note, I will say thank you, Lena, for your excellent presentation. Thank you for Patricia for your brilliant support. And thank you, everybody, for your participation. And we hope you enjoyed that. We will share a recording on YouTube in the next week or so. So thank you.
Thank you very much, Paul. That's great. Have a good day.